There's something almost poetic about watching a massive steel plate, thick as your fist, transform into a perfect cylinder. What we're seeing here is one of Central Europe's finest engineering firms working with a steel plate 4 3/4 inches thick, nearly 10 feet wide, destined to become a cylinder with a 55-inch diameter. For those of us who remember when heavy industry was the backbone of manufacturing, this is the kind of craftsmanship that built the world we know. The star of this operation? The plate rolling machine. And let me tell you, this Italian marvel is about as perfect as metalworking equipment gets. The company's been perfecting this craft since 1946, right after World War II, when Europe needed reliable machinery to shape the infrastructure of the modern age. The machine operates on a 3-roller pyramid principle, which has been the gold standard for rolling heavy plates since the Industrial Revolution, though the precision we're seeing here would have blown the minds of craftsmen from that era. Here's how this beautiful process unfolds. A steel plate, which has been preheated to reduce brittleness, gets positioned between 3 massive cylindrical rollers arranged in a triangular configuration. The 2 bottom rollers are the driving force, rotating in synchronized harmony to pull the plate through, while the top roller, which can be hydraulically adjusted to within fractions of a millimeter, applies downward pressure, creating the curvature. Think of it like rolling out dough, except this dough weighs several tons and could support a building. The operator, working from a computerized control panel, inputs the desired diameter and thickness parameters. The machine's sophisticated sensors continuously monitor the bend radius, making real-time adjustments through hundreds of hydraulic cylinders. Remarkably, despite working with such massive forces, the machine achieves tolerances that would make a Swiss watchmaker proud. The plate makes multiple passes through the rollers, bending a little more each time, gradually approaching that perfect cylindrical form. This incremental approach prevents stress fractures and ensures uniform curvature along the entire length. As the plate begins its transformation, you can actually see physics at work. The outer surface of the bend stretches while the inner surface compresses, and the metal flows like frozen honey, maintaining its structural integrity while taking on this new shape. Now, let's step into the world of heavy forging, where tradition stretches back to the blacksmiths of ancient Rome. Except now we're working with hammers that make Thor's hammer look like a toy. What's especially mesmerizing is the combination of raw power and surgical precision. We're watching parts being forged that can weigh up to 250 tons. The process begins long before the hammer ever strikes. Steel ingots, fresh from the mill, are slowly heated in gas furnaces to temperatures around 2,200 degrees Fahrenheit. This isn't a rushed process. Depending on size, heating can take anywhere from 8 to 24 hours. Once the steel reaches that perfect forging temperature, glowing that unmistakable orange-yellow color that means it's ready to flow, the real dance begins. Massive manipulators, essentially industrial robotic arms that can rotate and position these multi-ton pieces with remarkable delicacy, move the workpiece under the forging press. Both hydraulic presses and mechanical hammers are used, depending on what the job demands. A hydraulic press applies slow, steady pressure, ideal for ensuring the force penetrates deep into the heart of the piece, eliminating any internal voids or inconsistencies. The mechanical hammer, on the other hand, delivers rapid blows that shape the surface and create specific forms. The forge master, a craftsman whose skills require decades to develop, orchestrates this symphony of heat and pressure. Between each strike or pressing, the piece rotates, gets repositioned, and sometimes reheated. This is called open die forging, because unlike closed die forging, where metal is compressed into a specific shape, here the masters are literally sculpting the metal through repeated strikes and pressure applications, gradually drawing it into the desired form. Each strike refines the grain structure, making the steel stronger and more reliable than anything achievable through casting or machining alone. Now let's move on to modern precision forging, which has adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small batch artisan forging. The process starts with steel bars, often supplied in coils, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion, but within seconds a steel billet placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. The secret lies in electromagnetic induction, discovered by Michael Faraday way back in 1831, but only practically applied to industrial heating in the early 20th century. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit. Depending on the steel grade, the billet moves to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. What's remarkable is the speed and precision of modern forging presses. We're talking about machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. There's something deeply satisfying about watching skilled craftsmen build storage tanks. The process begins with selecting and cutting steel plates. Modern fabrication shops use CNC cutting tables, plasma or laser, that can slice through thick steel plate with remarkable precision, following computerized patterns that ensure minimal waste. But before any cutting happens, there's meticulous layout work, figuring out how to arrange different components to get the most from each plate. It's a puzzle that combines geometry, efficiency, and materials science. After cutting, the components move to rolling and forming operations. Tank shells typically need to be cylindrical, which means flat plates must be rolled into curves using 3-roll bending machines like the ones we saw earlier. The edges of these rolled sections are then prepped for welding, usually with beveled cuts that let the weld penetrate completely through the material's thickness. The welding process, that's where the craftsmanship really shines. Tank fabrication typically uses submerged arc welding for the main seams, a process where the arc works under a blanket of granular flux, protecting the weld from atmospheric contamination while allowing deep penetration and high deposition rates. End caps, whether they're flat, dished, or hemispherical, get fitted and welded on, and then comes the real test, hydrostatic testing. The completed tank gets filled with water and pressurized above its operating pressure to verify integrity. Any leaks or weaknesses show up here, not during service, which could be catastrophic. Let's wrap up with the 3-roll plate bending operation, because there's something fundamentally impressive about watching these machines transform flat steel into curves with such apparent ease. The 3-roll bending machine is one of those elegant engineering solutions that's remained fundamentally unchanged for over a century because, simply put, it works beautifully. The machine consists of 3 essential rollers arranged in a pyramidal or triangular configuration. The 2 bottom rollers are drive rollers that grip and feed the plate through the machine, while the top roller, which can be adjusted up or down hydraulically, provides the bending force. The beauty of this setup is in its simplicity and efficiency. By varying the top roller pressure and making multiple passes, you can achieve a wide range of diameters and even create nearly perfect circles. The process itself is mesmerizing to watch. The plate enters between the rollers, and as they rotate, you can literally see the flat material take on curvature. For thicker plates or tighter radii, multiple passes are necessary, with each pass increasing the curvature incrementally. Modern machines can handle impressive specs. Plates several inches thick and many feet wide, bending them into cylinders or cones with remarkable precision. The rollers themselves are precision-ground, hardened steel, designed to maintain their shape under enormous loads. This technology represents a perfect marriage of time-tested mechanical principles with modern control systems, creating tools that are simultaneously powerful and precise, capable of forming the steel that builds our world. What if I told you there's a metal that's 15 times rarer on Earth than gold? And to mine just 1 ounce of it, you need to process 10 tons of ore. A metal whose entire annual supply would fit in an ordinary room, while all the gold in the world would fill 3 Olympic-sized swimming pools? Every year, the world produces only 180 tons of platinum. That's 17 times less than gold. South Africa produces 120 tons, 74% of global production. Russia's in second place with 23 tons. To extract 1 ounce of platinum requires processing 10 tons of ore, while for gold, just 2 to 3 tons. The Merensky Reef, Upper Group 2, and Platreef contain only 2 to 10 grams of platinum per ton of ore. After flotation, the concentrate is heated to 1500 degrees Celsius to burn off iron and sulfur impurities. Then they use aqua regia, a mixture of nitric and hydrochloric acids, to dissolve the platinum. The concentration of platinum in Earth's crust is only 0.5 parts per million. Stick around till the end. You'll discover a secret that even jewelers won't tell you. Picture an underground mine several miles deep somewhere in South Africa, in the Bushveld province, home to the world's largest platinum deposits. These aren't open-pit mines. They're narrow tunnels blasted through rock up to 2 miles beneath the surface. Here, platinum is extracted from thin layers, reefs, that stretch for hundreds of miles but measure just 6 inches to 5 feet thick. 3 main reefs: the Merensky Reef, Upper Group 2, and Platreef. The Merensky Reef, discovered by Hans Merensky in 1924, has historically dominated global platinum production. Here, platinum reaches its highest concentration, 50 to 60% platinum group metals. Upper Group 2, a chromite-rich reef, more stable but with lower gold, copper, and nickel content. Platreef, a wider reef with lower platinum grades but higher base metal content, roughly 5 times more. Miners drill holes into the reef walls and pack them with explosives. After detonation, the shattered rock containing platinum and other metals is transported to the surface for processing. The ore gets crushed, then goes through flotation. That's a process that separates minerals based on how they stick to air bubbles in water. Mills grind the ore down until 60% of the particles pass through 75 micrometers. Then the ground ore gets mixed with water, and collector reagents are added, things like xanthates and dithiophosphates, which make the sulfide minerals containing platinum hydrophobic. Water repelling. Air gets pumped through the mixture, creating millions of tiny bubbles. The hydrophobic particles containing platinum stick to the bubbles and rise to the surface, forming a froth that gets skimmed off. Hydrophilic waste rock particles stay at the bottom. Platinum in Merensky ores is closely tied to base metal sulfide minerals: copper, nickel, and cobalt. The platinum group metals are present either as discrete platinum group minerals included in or attached to the sulfides, or in solid solution with the sulfides. The base metal sulfide minerals in Merensky: pyrrhotite, pentlandite, chalcopyrite, and traces of pyrite. After flotation, the concentrate still contains less than 1% platinum. Now, the concentrate heads to the smelter. It's dried and then heated in electric furnaces to temperatures exceeding 2700 degrees Fahrenheit. Air is blown through the molten metal to oxidize iron and sulfur impurities. Sulfur oxidizes to sulfur dioxide and gets removed as exhaust gas. Iron oxide is removed as phyolite slag. Platinum's melting temperatures are significantly higher than other metals due to the presence of chromium, which makes them incompatible and requires special furnace design. The power capacity of platinum smelting furnaces reaches 19.5 megavolt amperes and 68 megavolt amperes. Energy consumption runs 800 to 850 kilowatt hours per ton of concentrate. Platinum's high melting point means impurities like iron burn off, and the result is a powdery sludge of platinum group metals: rhodium, iridium, ruthenium, and osmium, plus platinum itself. The converter's slag phase contains significant amounts of trapped platinum metals and gets recycled back to the smelting furnace to recover those captured metals. The converter mat gets cooled down, crushed, and processed at a base metals refinery. Here, hydrometallurgical processes dissolve the copper and nickel, leaving behind a residue rich in platinum group metals. This platinum metals residue heads to a precious metals refinery, where various solvent extraction and precipitation methods separate out the individual metals. Getting pure platinum requires further refining. Typically, this involves aqua regia, a mix of nitric and hydrochloric acids in a 1:3 ratio. Aqua regia is one of the few acids that can dissolve platinum. When the concentrate is treated with aqua regia, the acid produces chlorine, which bonds with the platinum, forming chloroplatinic acid. The final step uses ammonium chloride to convert the chloroplatinic acid into ammonium hexachloroplatinate, which can be calcined to yield pure metallic platinum. Platinum content in the residue after hydrometallurgical processing can reach 5,900 ounces per ton. That's an enrichment of nearly 500 times compared to the original flotation concentrate. Now, a bit of history. In 1735, Antonio de Ulloa and Jorge Juan y Santacilia witnessed indigenous Americans mining platinum while the Spanish traveled through Colombia and Peru for 8 years. Ulloa and Juan found mines with whitish metallic nuggets and brought them back home to Spain. Antonio de Ulloa returned to Spain and established the first mineralogical laboratory in Spain and was the first to systematically study platinum, which happened in 1748. In 1783, French chemist François Chaboneau was the first to obtain a pure sample of platinum metal. In 1801, English scientist William Wollaston invented a method for efficiently extracting the metal from ore. Growing demand for the metal led to the discovery of major deposits in the Ural Mountains in 1824 and in Canada in 1888. This ultimately led to geologist Hans Merensky's discovery of the largest platinum deposit on Earth in 1924. Platinum is primarily used in automotive catalytic converters. In 2014, out of 218 tons of platinum sold, 98 tons, 45%, went to vehicle emission control devices. 74.7 tons, 34%, to jewelry. 20 tons, 9.2%, to chemical production and petroleum refining. 5.85 tons, 2.7%, to electrical applications like hard disk drives. The remaining 28.9 tons went to various other minor applications, such as medicine and biomedicine, glass-making equipment, investments, electrodes, anti-cancer drugs, oxygen sensors, spark plugs, and turbine engines. The most common use of platinum is as a catalyst in chemical reactions, often in the form of platinum black. It's been used as a catalyst since the early 19th century, when platinum powder was used to catalyze the ignition of hydrogen. In automotive catalytic converters, it completes the combustion of low concentrations of unburned hydrocarbons from exhaust gases into carbon dioxide and water vapor. Platinum is extremely rare on Earth, occurring at a concentration of just 0.05% in the Earth's crust. Platinum often occurs chemically unbonded as native platinum and primarily as an alloy with other platinum group metals. Most commonly, native platinum is found in secondary deposits among alluvial sediments. The alluvial deposits used by pre-Columbian peoples in the Chaco Department, Colombia, are still a source of platinum group metals today. Another major alluvial deposit is located in the Ural Mountains, Russia, and it's still being mined. When comparing the rarest precious metals by annual mine production, platinum is far rarer than gold. We're talking about more than 15 times rarer by annual output. In 2018, silver, gold, and platinum mine production totaled 860 million ounces, 108 million ounces, and 6 million ounces respectively. Producing a single ounce of platinum requires about 10 tons of ore. For comparison, gold needs around 2 to 3 tons of ore to produce 1 ounce, while silver takes 5 to 10 tons per ounce. Global demand for platinum in 2023 was estimated at 7.5 million ounces. The world's largest platinum producer, Anglo-American Platinum, produced 1.75 million ounces of platinum in 2023. Russian company Norilsk Nickel produced 593,000 ounces of platinum in 2022. Every year, an additional 2 million ounces, 60 tons of platinum, comes primarily from recycling auto catalysts and jewelry. What makes platinum stand out is just how difficult it is to extract. Platinum mining is extremely labor-intensive. The KEL process represents a potentially significant improvement in platinum concentrate processing technology from an economic standpoint through dramatically reduced energy costs. Compared to matte smelting, electricity consumption drops by 82%, and overall carbon dioxide emissions decrease by 70%. And so, having traveled from a thin reef deep underground in South Africa, through blasting, crushing, flotation with millions of bubbles, through smelting at 1500 degrees Celsius, through dissolution in aqua regia, through precipitation with ammonium chloride and calcination, platinum is born. A metal 15 times rarer on Earth than gold, requiring 10 tons of ore to be processed for a single ounce, whose entire annual supply, just 180 tons, would fit in a single room. A metal that catalyzes chemical reactions, cleans the exhaust of millions of cars, and adorns fingers with jewelry that never corrodes.
What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, then gets reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore flare up like tiny controlled earthquakes. Zinc, the fourth most consumed metal in the world after iron, aluminum, and copper. 12 to 13 million tons of zinc are produced every year. 60% of all zinc goes into galvanizing steel. Without it, bridges, cars, and buildings would rust many times faster. But here's the shocker. At 2700 degrees Fahrenheit, zinc literally turns into vapor and disappears into the air, and then condenses back into liquid metal. In this video, you'll learn things you never suspected, and at the end, the main secret will be revealed that will forever change how you think about zinc.
Picture a massive underground mine somewhere in China, Australia, or Peru, the world's biggest zinc producers. These are entire underground cities stretching hundreds of feet, sometimes even miles beneath the Earth's surface. We're not talking about simple holes in the ground. This is a network of tunnels, shafts, ventilation systems, and lift shafts. Powerful drilling rigs bore holes into the rock, blast holes. Explosives get packed into these holes.
After a carefully controlled blast, massive volumes of rock break apart. It's like a spectacular but controlled earthquake in miniature. Dusty air gets quickly cleared by powerful ventilation systems, which also pump fresh air down to these depths. The broken ore then gets loaded onto massive underground trucks or conveyor belts using front-end loaders. It's a genuine underground transportation flow, continuously moving, hauling tons of ore to the central lift shafts. From there, the ore rises to the surface using powerful elevators or specialized conveyor systems, climbing hundreds of feet straight up.
At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock, containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a concentrator plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore into crushers that, with a deafening roar, break them down into smaller pieces. Then this crushed ore moves into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore is ground down to an extremely fine powder, almost like flour. This is critically important to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder is mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. The zinc mineral particles latch onto these bubbles and rise to the surface, forming foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can contain up to 60% zinc. Since zinc is often found alongside lead, the processing plant may run multiple flotation cycles to separately extract zinc concentrate from lead concentrate. The zinc concentrate you end up with still isn't pure metal. It has to go through metallurgical processing to get metallic zinc. And now we enter the world of extreme temperatures. If the pyrometallurgical method is used, the zinc concentrate first undergoes roasting. The concentrate is heated in specialized furnaces at temperatures around 1800 degrees Fahrenheit.
This removes the sulfur, which is part of the sulfide ore, converting it into zinc oxide. The sulfur transforms into sulfur dioxide gas, which is captured and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable product. Next, the zinc oxide is mixed with coal and heated to even higher temperatures, over 2200 degrees Fahrenheit, sometimes even 2700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process occurs. The carbon strips oxygen away from the zinc oxide, freeing up pure metallic zinc. And this is where that incredible wow moment of vaporization happens. At these temperatures, the metallic zinc transitions into a gaseous state. It evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is significantly higher, zinc literally turns into vapor, which rises and gets collected in specialized condensers.
The vapor cools and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or granules. Now for the history. Zinc has been known to humanity for thousands of years, though it was only isolated as a distinct metal in the 16th century. Ancient civilizations used brass, an alloy of copper and zinc, without knowing it actually contains zinc. In India and China, people learned to smelt zinc as far back as the Middle Ages. But modern industrial zinc production only began in the 19th century with advances in smelting technology. The primary use of zinc: galvanizing steel. Around 60% of all zinc produced goes toward protecting steel from corrosion. Zinc coating on steel creates a sacrificial layer. The zinc oxidizes instead of the iron, protecting the structure. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a surge in resource demand. (15 to 20% of zinc goes into making alloys like brass and die-casting alloys. These alloys end up in car parts, home appliances, toys, plumbing, and electronics. Another 10 to 15% becomes zinc oxide and other chemical compounds. Zinc oxide has crazy wide applications: sunscreens and cosmetics, paints, ceramics, rubber manufacturing, and even livestock feed supplements. Its antibacterial and protective properties make it a universal ingredient. The rest of the zinc gets used in batteries, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, because zinc is absolutely vital for the human immune system. As for prices, like most commodities, zinc prices swing with global supply and demand, economic cycles, and what's happening in the biggest producer and consumer countries. Yet demand for zinc remains steady or growing, driven by urbanization, infrastructure development, and the need to protect metals from corrosion worldwide. This makes zinc a crucial indicator of global economic health. Zinc ranks as the fourth most consumed metal on the planet, after iron, aluminum, and copper. That alone tells you just how massive its importance is for the global economy and industry. Annual worldwide zinc production sits at roughly 12 to 13 million metric tons. These are enormous volumes, underscoring its irreplaceability across hundreds of applications. The primary zinc mining regions are China, Australia, and Peru. These three countries together account for a significant share of global zinc ore extraction, making them key players in the market. For instance, China isn't just the largest producer, it's also the world's biggest zinc consumer, reflecting its powerful industrial expansion. Other major producers include India, the United States, Mexico, and Canada. When it comes to reserves, the U.S. Geological Survey estimates global zinc reserves at roughly 250 million metric tons. On top of that, there are what's called resource spaces, potential deposits that haven't been explored yet or aren't economically viable to mine right now. Those are estimated at over 1,800 million tons. These numbers show that zinc, unlike some rare metals, will last for many decades, even with growing consumption. Most zinc is mined from underground operations, entire subterranean cities stretching hundreds of feet, sometimes several miles beneath the Earth's surface. These aren't just holes in the ground, they're networks of tunnels, shafts, ventilation systems, and hoisting shafts. It all starts with exploration. Geologists, like detectives, hunt for ore bodies, sections of rock where the concentration of zinc, which, by the way, usually occurs as sulfide ore, like sphalerite, and almost always comes with lead, silver, and sometimes copper, is high enough to make it worthwhile. Once a deposit is discovered, mine construction begins. This involves sinking vertical shafts, which provide access to the ore, lift materials up, lower equipment down, and creating horizontal tunnels, or drifts, that lead directly to the ore veins. The actual ore extraction process? Dynamic, risky. Miners use specialized equipment, powerful drilling rigs that bore holes into the rock, called blast holes. Explosives get packed into these holes. After a carefully controlled detonation, massive volumes of rock shatter. It's like a spectacular earthquake, in miniature, under control. And that's how, starting from an underground explosion, through crushing into powder, through flotation with millions of tiny bubbles, through roasting at 1800 degrees and reduction at 2700 degrees, where the metal literally turns into vapor and vanishes into thin air, then condenses back into liquid zinc, a metal is born that shields steel from rust, makes bridges possible, cars, skyscrapers, without which the modern world would look completely different.
But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydro turbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydro turbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining, but the foundation of its strength, that's laid right there on the press. $80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys. Titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force.
The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013, China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons, a huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees. The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then the upper plate of the press begins its descent, slowly, almost ceremonially. But behind that calm lies 80,000 tons of force. Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans. Excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure.
Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing.
China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty. There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants, still running in defense plants today. The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it, the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, it's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.
The metal that powers the planet. Every second, 3 electric cars are sold worldwide. Every hour, 50,000 smartphones roll off production lines, and all of them depend on one element: lithium, the white gold of the 21st century. The lightest metal on Earth, which you'll never see in its pure form because it instantly explodes on contact with water. But it's what fires up your phone, drives electric vehicles, and will power humanity's future. How do salt lakes high in the Andes transform into an energy source for billions of devices? You'll discover why lithium is called white gold, how giant evaporation pools the size of a city work, and why a real geopolitical war has erupted over this metal. Watch until the end. The finale will reveal what's behind every percentage point of your smartphone's battery. This is the story of a metal that changed the world in just 20 years.
Lithium's story began in 1817 on a tiny Swedish island called Uto. A young chemist, Johann August Arfwedson, was analyzing a rare mineral called petalite when he discovered something strange. This was a metal, but incredibly light, lighter than water. Arfwedson named it lithium from the Greek word lithos, stone. Ironic, right? A stone that floats. In 1821, British chemist William Brand first isolated pure metallic lithium through electrolysis of molten salt. What he saw blew his mind. A silvery white metal so soft you could slice it with a knife like butter, and so light that a chunk of lithium actually floats on water. But that contact with water, it lasts maybe a second. Lithium instantly explodes into a violent reaction, hissing, smoking, and it can catch fire. For 150 years, lithium was just a lab curiosity. They used it in medicine to treat mental disorders, in glass and ceramic production. But everything changed in the 90s. In 1991, Sony released the first commercial lithium-ion battery. It was a breakthrough. Before that, batteries were heavy, short-lived, drained fast. Lithium-ion batteries turned out to be 3 times lighter and held their charge way longer. The portable electronics revolution began. Cell phones became compact, laptops became light, cameras became long-lasting. But the real explosion in demand happened in the 2010s when electric vehicles hit the market. Tesla, Nissan, BMW all built their cars on lithium-ion batteries. One electric vehicle requires 130 to 175 pounds of lithium. For comparison, a smartphone contains just 1/10 of an ounce. Demand for lithium jumped from 30,000 tons in 2010 to 550,000 tons in 2023, and that's just the beginning. Forecasts predict 3 million tons by 2030. Lithium transformed from a rare lab element into a strategic resource more important than oil. But where do you get that much lithium? On Earth, lithium isn't rare. It's the 33rd most abundant element. But here's the thing. Concentrated deposits, not so common. There are 2 main sources, hard rock and salt brines. Hard rock means spodumene, a rare mineral mined in Australia, Canada, Zimbabwe. But the future? It's in the brines. High up in the salt lakes of South America, at 10 to 13,000 feet above sea level, lie the planet's largest lithium reserves. It's called the Lithium Triangle: Bolivia, Chile, and Argentina. Bolivia's Salar de Uyuni is the biggest salt flat on Earth. 4,000 square miles of blinding white salt under an endless sky. Looks like a massive frozen lake. Beneath that salt crust, brine, containing about 9 million tons of lithium. That's half the world's reserves. Chile's Atacama, the driest desert on the planet. Here too, massive lithium deposits hide in underground brines.
Now, let's break down how lithium is actually extracted from these salt lakes. The process looks almost magical. First, they drill wells anywhere from 65 to 330 feet deep. Powerful pumps suck up brine from these wells, a salty liquid similar to seawater, but way more concentrated. A single liter of this brine contains anywhere from 300 to 1,500 milligrams of lithium. For comparison, seawater has just 0.17 milligrams per liter. The pumped brine gets channeled into massive evaporation ponds. Picture this, artificial lakes covering dozens of hectares. From above, they look like giant colored squares, blue, turquoise, green, yellow. The color depends on mineral concentration and microorganisms. These ponds are arranged in a cascade, like giant steps. The brine flows from one pond to the next, and at each step, the magic of evaporation happens.
Under the scorching sun of the high-altitude desert and relentless winds, the water evaporates, slowly, month after month. The Atacama receives less than a millimeter of rainfall per year, but the sun shines 300 days a year, perfect conditions for evaporation. The lithium concentration in the brine gradually increases. First, unwanted salts precipitate out of the solution, sodium chloride, sulfates. They're collected and removed. The process takes 12 to 18 months. Yeah, you heard that right. Over a year just waiting for the sun to do its work. During this time, the lithium concentration grows by roughly 20 times. What started as a weak brine transforms into a thick, oily solution containing about 6% lithium. The brine turns amber yellow, almost like honey. It's pumped into specialized tanks and shipped to a chemical plant. Here begins the final stage of transforming salt water into white gold. At the plant, concentrated brine is treated with sodium carbonate, basically baking soda. A chemical reaction happens and a white precipitate crashes out of solution, lithium carbonate. It's not the metal yet, but it's a crucial compound. The precipitate gets filtered, washed, dried. What you end up with are fine white crystals, like powdered sugar. That's why lithium's called white gold. It actually is white. Lithium carbonate gets bagged up and shipped all over the world. Most of it goes to China, Japan, South Korea, wherever batteries are made. But that's not the end of the road. To make batteries, you need lithium hydroxide. Lithium carbonate gets dissolved in water, treated with calcium hydroxide. You get a solution of lithium hydroxide, which then gets evaporated. What remains are white crystals of lithium hydroxide, the final product, ready for manufacturing battery cathodes. The whole cycle, from pumping brine to getting the finished product, takes about 2 years. There's another method for extracting lithium, from hard rock deposits. In Australia and China, they mine spodumene, a mineral that contains lithium. They blast the rock, crush it, grind it into dust. Then they heat it to 1900 degrees Fahrenheit in massive rotating kilns. At that temperature, the spodumene changes its structure, becomes more reactive. The roasted rock gets mixed with sulfuric acid. A violent reaction kicks off, releasing heat and toxic gases. The lithium moves into a lithium sulfate solution. This solution gets purified of impurities, treated with sodium carbonate. Lithium carbonate precipitates out, the same product as from the brines. But this method is way more energy intensive and expensive. You need high temperatures, massive volumes of chemicals, tons of waste gets generated. That's why the future belongs to brines. Even though right now about 60% of the world's lithium comes from hard rock, the balance is gradually shifting toward salt lakes. Now let's look at where all this extracted lithium goes. 75% of global production goes into batteries. A lithium-ion battery is a complex device. Inside are 2 electrodes, a cathode made of lithium oxide with cobalt or manganese, and an anode made of graphite. Between them is an electrolyte containing lithium salts. During charging, lithium ions move from the cathode to the anode and slide between the graphite layers. During discharge, they move back, and this flow creates an electrical current. Brilliant simplicity. Lithium is ideal for this because it's the lightest metal capable of giving up electrons. A single lithium atom weighs just 7 atomic units. For comparison, lead weighs 207. That's why lithium batteries are so light and energy-dense. A modern Tesla Model 3 electric vehicle contains about 24 pounds of pure lithium in its 1,060-pound battery. This battery can travel over 300 miles on a single charge. Beyond batteries, lithium is used in ceramics and glass production. It lowers melting temperatures and makes materials stronger. In metallurgy, lithium gets added to aluminum alloys, makes them lighter and tougher. In nuclear power, lithium produces tritium. In medicine, lithium carbonate is still used to treat bipolar disorder, stabilizes mood. Global lithium production in 2023 hit around 130,000 tons of pure metal equivalent. The major producers, Australia, 40%, Chile, 25%, China, 14%. Lithium prices rocketed from $5,000 per ton in 2020 to $80,000 in 2022, then crashed to $30,000. The market's volatile because demand is growing faster than supply. A real geopolitical battle has erupted over lithium. China's buying up deposits worldwide. The US is trying to build its own supply chain. Europe's hunting for alternative sources. And just like that, having journeyed from salt lakes high in the Andes through 18 months of evaporation under the merciless desert sun, through chemical plants and the most complex purification processes, lithium emerges into the world, the white gold of the 21st century, the lightest metal that powers modern civilization. This is the story of how humanity learned to turn salt water from ancient lakes into energy for billions of devices. Every time you charge your smartphone, get into an electric vehicle, or fire up your laptop, remember, inside beats a heart made of lithium, the metal for which we mine deserts and drain salt flats, the metal behind the energy revolution and the move away from oil, the metal without which the future of humanity is unimaginable. White gold extracted from snow-white salt lakes to power the planet with the energy of tomorrow. Lithium isn't just an element on the periodic table. It's the key to a future that's already here.